Talk to you guys today about the use of optical emission to study competing phases in the second Landau level. I'm here representing our group in the place of Dr. Aaron Prenzig, who unfortunately couldn't be with us today because he's recovering from an illness. Before getting started, I'd like to thank all of our collaborators and the funding agencies which made this work possible. So just a quick look at what we're going to be talking about today. I'm going to discuss a little bit about the background, the physics of the second Landau level, the competing phases, and the methods we use. Why it is we use optical spectroscopy, and how in this experiment we used light scattering, resonant elastic and inelastic, to lend greater meaning to the results from our optical emissions before getting into the results themselves. Quick note: the optical emissions that we use in our work is actually from the second Landau level, as opposed to the first. I know that a few of you have done work with optical emission from the first Landau level. Actually, one of the results we're going to see is that the results themselves are qualitatively quite different. Anyways, let's get started. So as most of you know, the second Landau level is a really rich field of study because it displays not only fractional quantum Hall states, but also reentrant integer quantum Hall states, which arise from partially ordered phases, or thought to be the bubble or stripe phase, which also result in.
Can I ask a question?
Yes.
Do you work in the solid state?
I do.
Okay. Could you give like 4 sentences to describe kind of something else about? So the fact that I don't know that you work in the solid state, you say like 4 sentences about like the physical system you live in. Is it
Oh, I'm gonna get to that in a minute, but yeah, we're looking at a symmetrically doped quantum well in gallium arsenide.
Thank you.
Yeah, we're sorry for not mentioning that, but yeah, we're looking at a simple two-dimensional electron system confined to a symmetrically modulation doped quantum well in gallium arsenide. But yeah, and so yeah, the transport conducted on this system shows in the second Landau level both the reentrant integer quantum Hall states, which arise from things like things postulated to be electron solids, and so the interaction of, so not only does it display both of these as ground states, but there's fascinating interaction between them, such as the anisotropic fractional quantum Hall state observed famously here in the paper by the Eisenstein group. And the last one was the results before were from the PRL by Deng et al. And actually the group that's who's here today with us, and yeah, these are from the PRL from regarding the transport of the scale of the reentrant states. But anyways, these states are known to interact with one another, are known to form anisotropic fractional quantum Hall states when you introduce anisotropy by putting in an in-plane magnetic field, as shown here from the results from the Nature paper by Xie et al. Anyways, some of the big advantages of using optical probes, or some of the big contributions of them, is that we instead of looking at the edge conductance, we actually look directly at the bulk. So when we use resonant Rayleigh scattering, we're really probing the vacancies in the conduction band, and the use of resonant elastic light scattering enables us to not only probe the excitation spectrum, but actually distinguish between charge and spin modes. And finally, and what we're looking at today is the optical emission, which also allows us to look specifically at not only extended but also localized states and look at everything simultaneously. So Here's just a look at our samples. They're grown by our collaborators at Princeton and Purdue. The two samples we're looking at had densities close to 3 times 10 to the 11 electrons per centimeter and have a mobility of about 20 to 25 million. The quantum well itself is confined to 300 angstroms in order to confine it to the lowest quantum well energy level. Our experiments are conducted in a dilution refrigerator. Our samples are mounted onto a cold finger, which is in this dilution refrigerator, which has windows which allow for optical access and allow us to perform some light scattering. The sample is tilted slightly, is given a slight tilt so that to avoid reflected light coming back in and destroying our signal especially when we conduct light scattering experiments. One side effect of this non-zero tilt is that there is a non-zero in-plane magnetic field in all of our studies, and varying this tilt, which we've done in experiments since this actually, and which has been done extensively again by lots of group, the Chatti group here, is very it yields some very interesting results about the roles that pinning plays and other things like the spin polarization of the phases. It's so just a quick word about so here's an overview of just the resonant Rayleigh scattering, that just to for completeness sake, it's in general we've used this not only to probe the nature of some of the different signals we see from optical emission, but also it allows us to it's allowed us also in other experiments to look at the isotropy or anisotropy of the electron systems we're studying. We're able to, the resonant elastic light scattering, it makes it a very easy task to probe single particle excitations, and whose matrix elements is shown here. But more importantly to this talk is the ability of probing collective excitations, which are a third order process. So there's both an absorption and an emission resonance that we can utilize. And the one side effect of using of exciting collective modes, which allow us to both view all sorts of collective excitations, is that we also are able to exploit the presence of weak residual disorder in breaking wave vector conservation in order to actually probe excitations that are further out in the spectrum, whose wave vector is much larger than the difference between the incident and scattered light, and allows us to really take a look at all of the roton modes as well in the excitation spectrum of the states we study.
Can you give us a sense of scale for omega?
Oh, it can vary quite a lot. What we're looking at right now is we're looking at in this experiment in these experiments I should say, we look at omega on the order of the Zeeman energy. But I mean it can be significantly larger than that. In fact, Professor Pinzik famously used this, also exploited the inter-Landau level excitations using resonant and elastic light scattering. So it needn't be confined, but yeah, typically we use it on the scale of the Zeeman or cyclotron energy. Yeah. So yeah, the one we're looking at though is mainly we're going to look at the excitations from the spin wave, and the spin wave is basically the collective it's a collective spin flip excitation. It's propagating through a system. The Larmor theorem states that at zero wave vector for a spin rotationally invariant system, and a system that doesn't violate that doesn't violate the inversion symmetry is very it's at the Zeeman and it's at the Zeeman energy, and typically we will use it either to probe the Zeeman or the exchange energy, and thanks to the fact that the difference in the resonances, we're actually able to distinguish between one mode and the other when we're looking at cross-polarized resonant inelastic light scattering. This method, this spin wave mode is actually also extremely useful in determining the exact filling factor, the exact magnetic field for filling factor 3, because it displays an incredibly strong sensitivity to the spin polarization of the electron system. So if you're above filling factor 3, then there's already spin down. So there's fewer possible spin flips available because there's already spin down electrons, and if you're below, then there's simply fewer electrons with a spin flip mode that you can probe. So this is actually how we typically determine the closest odd integer filling factor, and which we will use to basically which we use as the basis of what our filling factor will be throughout the experiment. Now, it's also worth noting, as this is from these, as you can see from these results from a paper we published in 2015 in December. It's all these spin wave modes, along with all of the other modes, actually just in the filling factor range studied, are very sensitive to the presence of the incompressible fractional quantum Hall states. So in general, the compressible fractional quantum Hall fluid might have or in this case it might be display it might break spin rotational invariance. It might have some sort of spin rotational order which would allow for lower energy modes, which would generally which would soften and which would completely soften the mode, would let the energy of the excitations vanish, but the lowest lying excitations vanish. But here, at the fractional quantum Hall states, you have the incompressibility. The incompressibility results in a well-defined spin mode at these fractional quantum Hall states here, shown here, and just to show as we move away from odd integer filling factors, we see that we can see the softening of the spin wave mode, which we attribute oftentimes to the breaking of spin rotational invariance and possibly the formation of spin textures, and that's shown here in the 2008 paper from our group by Gallet et al., where these spin textures melt away as you increase temperature to the point that the spin wave at the Zeeman energy is recovered once you're at high enough temperatures. So here is just an overview of our optical emission results. As I mentioned earlier, we're focusing on those of the second Landau level. Basically, there's two features we observe. We observe a feature that disperses linearly in magnetic field, whose energy disperses linearly in magnetic field, which I call the X peak, and then which also displays a somewhat trivial filling factor dependence, or its intensity does. And there is a redshifted sort of multiplet of peaks, which I call the L peaks, which are shown here in the below the X peaks. Those we interpret as arising from phases, for reasons we'll get into from different, more collective phases of the second Landau level, reasons we'll get into shortly. Here's sort of a closer look near 5/2. The peak here, as you can see, it's really this is not. We're going to see clear examples of this, but these L peaks are always consist of multiple are always appear to consist of multiple peaks whose intensities and relative intensities change significantly with magnetic field. Now, when we perform resonant Rayleigh scattering, you see there's absolutely no change. There's no enhancement that occurs in the presence of these peaks as there would be if there were single particle transitions that were possible there. But at this X peak, there's a very clear enhancement of the resonant Rayleigh scattering, and this is really true at all filling factors. And this is interpreted, along with the linear dispersion of the X peak's energy with magnetic field, is interpreted as possible evidence that it arises from single particle like transitions, or single particle excitonic transitions. Here's just an overview of the fitted results, where we've discussed a little bit the X peaks, but now looking at the composition of the L peaks, what you see is it's typically we fit these the fitting process we used was with Lorentzians and in a couple of cases Gaussians, and as you can see, there's a very strong filling factor dependence on the intensity, and as you get closer to particularly near the 7/3 filling factor, these peaks end up the interplay becomes really striking. And but first we're going to quickly look at the results near filling factor 3. So we basically see two peaks here, which I've called the L0 and L1, where the L1 really corresponds to what happens when you move away from filling factor 3, when you decrease from it. It also increases somewhat in intensity with increased in-plane magnetic field, and also it corresponds generally with a softening away of the spin wave mode from the Zeeman energy. So the effective G factor of our system as it decreases, the intensity of the L1 increases. So there appears to be a very strong link there, and it's worth noting that with temperature, the L0 mode, which is really strong near the insulating filling factors near nu equals 3. While this one it increases with temperature and displays a somewhat strong temperature dependence, the L1 mode appears not to. So the L1 mode appears to arise from the formation it appears to be marked have a marked connection to some sort of anisotropy, and it's possibly the formation of. I mean, it's possible that it might be the formation of spin textures, but it's not entirely sure. Whereas the L0 peak is it appears to just be resulting from insulating phases. It's worth noting that at even higher temperatures, the L1 peak really collapses, and the L0 peak just keeps increasing in intensity.
What's the evidence that he's saying?
Well, the evidence, the filling factors during which it's prominent correspond to filling factors where in analogous transport experiments there's anisotropy in transport. It also corresponds more strongly to in-plane magnetic fields, and which also has been known to link, and also the softening of the spin wave. So it's really this combination of things. Though it is worth noting that it's still something that really is to be looked into further. But yeah, that's so. The results near the results near 7/3, or where the L2 peak is most dominant. This is the one which is in a sense the most mysterious to us, because the results are really the least clear to some extent. But what we can say is that it also appears to be linked to some loss of spin rotational symmetry, because the redshift in the spin wave is fairly strong there in its presence whenever it's prominent. The redshift in the energy of the spin wave is fairly large, and it also actually displays some limited temperature dependence above this 650 millikelvin. It's worth noting, though, also that that whenever it is prominent, that it's prominent when these fractional quantum Hall phases are observed, and the temperature dependence of this system is such that as it decreases and the next competing phase increases, as temperature is increased, as the L2 decreases and the L3 increases, that corresponds to the disappearance of the 2/3 fractional quantum Hall, or 2 + 1/3 fractional quantum Hall state, because this EG is actually interpreted. It was shown in the paper by Rostaro et al. To arise really from charge modes of the 7/3 state, and so as this decreases, this vanishes, and the L2 decreases and the L3 increases in intensity. As you sort of see that dynamic, you see the disappearance. So there's some connection there. So this brings us, though, then to this other. So we're not quite sure what exactly this is, but we think it might be some other anisotropic mode that supports the fractional quantum Hall states. But the last mode we're going to discuss, or the last results we're going to discuss, are those concerning this so-called L3 emission, which corresponds to a filling factor range in which there's really no observation of fractional quantum Hall states. And in fact, as you saw earlier, as the L3 as its intensity increases, the fractional quantum Hall states. The fractional quantum Hall states at the temperature, at the filling factors at which it was observed, vanish, and so it seems to correspond to a competing phase with fractional quantum Hall states. It's also the only phase. This phase, is the dominant phase or appears to be the dominant phase, at the only filling factor at which we observe a spin wave not associated with any fractional quantum Hall or even reentrant integer quantum Hall phases. This one's also a very interesting phase in that it survives to even higher temperatures, as does this mode and sort of this mode alone. So it appears to be it appears to be a spin polarized phase, not just because of the presence of the very prominent spin wave in association with it, but also because in some of the inelastic light scattering, which I haven't included here, unfortunately, in some of those experiments, we actually observe this peak and this one as we observe the luminescence from those peaks at excitation energies where only one spin is excited in the valence band. So in any case, it's as of now we haven't determined exactly what it is, but we're actually seeing some promising signs that it might be linked to potentially the predicted electron solid bubble phase. But it's still too early to say, and I won't get into that the rest of those results at this point unless there's interest. But anyways, that concludes this talk. Basically, yeah, we've looked at the emission of optical emission from the second Landau level to study this filling factor, competing phases of this filling factor range. You know, the temperature dependence suggests these arise from these ordered phases because these phases really exist at a much higher temperature range than any fractional quantum Hall states, and the filling factor dependence is also, while very pronounced, not as pronounced as those of fractional quantum Hall states. And so, yeah, if there's any questions now, that would be the time. Yeah.
I didn't quite get this idea about spin wave softening. Could you show me the experimental signature of that?
Oh yeah.
And what you're increasing and what is softening?
So softening refers to when the spin waves decrease in energy as a result of the formation of the breaking of spin rotational invariance. Now that you could think of that
Very what?
as the filling factor. Oh, sorry. When you move the filling factor away from a filling from an integer filling factor, you don't only just lose spin up or gain spin down electrons. It actually becomes energetically favorable to form spin textures instead. And so what you get there is you get sort of a reduction in the effective G factor, and so that's why they soften. Of course, yeah. The order gets overridden with temperature, though. So yeah.
But this more filling factor than I thought you said that the spin polarization is very small, right? This is not even 3; it's 1.06.
Well,
I thought you say you will gain. Mostly you have a spin polarized, but up to maybe 3, then you begin to have some flip spin.
Oh, well.
Or do you have separate measurement on the spin content or the quantum Hall state?
Well, I mean, are you asking specifically about near filling factor 1? Because I was talking.
These experiments.
These experiments specific. The experiments like this one. Like the experiments in the second Landau level or the first? Oh, sorry. The ones I was just showing. These right here are in the first Landau level. So the spin flip results from, you know, you're in the 0th Landau level, so you're starting to populate the spin down branch. I mean, is that the question?
Well,
or because
later on you may also mention that there are some spin there might be evidence with spin density waves.
Oh,
so in those cases, I would have thought that then you would have some up and down non-zero opposite spin fractions. So I was wondering whether there are other measurements to determine the spin content.
well, I mean, there's been nuclear magnetic resonance experiments have also measured the spin content, but in general, actually, if maybe this, I feel like maybe this might. I feel like I'm not fully understanding the question. 1 second. So let me just go to this slide afterwards that I've prepared. I think it's is it you, or no? That's not you. This is it. Yeah. Sorry, just a moment.
I guess my question, first simple question, is whether how spin polarized the system is. Second is that if the system is not spin polarized, it's not fully spin polarized, and then what are the possible what your experiment can say about the possible spin structures of the system?
Well, so yeah, the system is. I mean, naively, you would expect it to be spin polarized in the lower spin branch when the Fermi energy. So the question as to whether or not it's spin polarized, to some extent, was addressed briefly in this PRL by our group by Versbauer et al. And basically, if you look at the top figure, as you go down the this line is the intensity of the spin wave signature here on the top line. That would represent fully spin, or what you would expect to be fully spin polarized. And so when we move away from the fully spin polarized, a lowered intensity might be able to tell you, first of all, that you're no longer fully spin polarized, but also it might be able to say something with regards to or reduced energy might tell you something about the existence of some order. And actually, there's a paper that I didn't reference. It's a 2010 paper by Drozdov et al. And it addresses mainly near filling factor 3. But one thing that you would be able to see is you'd be able to see this redshifted mode, as well as some additional modes if you're lucky, I guess. If you're fortunate enough to see if the experimental setup is optimized to see it, and you'd see additional modes that would state the presence of some degree of order, and not just the fact that you have some spin down as well as some spin up. If that, as well as just spin up. If that answers your question, I'm not sure. Yep.
When you showed plots of the luminescence intensity, you may have said something, but am I supposed to understand this as recombination with a localized hole at some impurity, or is it a free? We're actually looking at the decay of an exit time with an unbound, with a free hole in the valence band.
That is a good question. Sorry, 1 second. I'm just going to go back to the. In general, I would have. We haven't fully finished conclusively answering the question as to whether or not the holes themselves are localized when we do the photoluminescence in this experiment. But it appears one thing that I haven't shown here is the power dependence, and oftentimes simply the presence of the power dependence would yield in this case, for example, well, for some of the phases it would yield a significant increase in the it would yield a significant increase in the peak's intensity, and where temperature dependence wouldn't.
So when you increase the power, you get more recombination.
Yeah, and especially more recombination relative to the X peak. It's the recombination is greater relative to the supposed extended single particle, and so I would say that. I would say in answer to your question, it's probably they're likely localized holes, but I think that I think that in general, part of the reason that the signature is so small is that they aren't full. They're not all localized holes. I guess that's I don't think I'm really answering the question properly, but the short answer is I'm not sure. Yeah. Yeah, but sorry, was there another?
Identifying these L peaks, is there any polarization dependence that you can use to interpret what's going on?
Unfortunately, we haven't looked at the polarization dependence of, or the polarization of the dependence of the light. But one thing we have seen is when we look at the results from resonant inelastic light scattering, we also see luminescence. And because we look at we're looking at experiments near resonance, near where only one spin orientation of the hole has been excited, the fact that we do in fact see, for example, the L3 peak, that one we're fairly sure comes from a spin polarized phase, because that peak, for example, is visible when we're only exciting one spin polarization of holes. But yeah, further studies of this would be a little bit more might prove a little bit more time intensive, and yeah, we'll hopefully they'll get done. But, yeah.
Sorry, but it seems that a strong, important point you emphasize is that there is a mode that continues even though the quantum Hall stays destroyed by temperature. So is that correct? And that only occurred for filling factor of greater than 3 and did not occur for solar filling factor?
Well, no, it actually occurred for a filling factor significantly less than 3. It occurred, the filling factor, it's a very long story, and we can talk about it at length later, because but the short of it is, it occurred as a result of this phase here, the phase associated with L3, whatever that is, or whatever they are, if I'm being completely honest from those results. The higher the temperature, at the higher temperatures, we don't see 7/3 spin flip or a lot of the spin flips. When I say higher temperatures, I mean specifically near 1 Kelvin. But what we do see is this spin mode, and so I think that this phase survives and is even prominent at higher temperatures where and it's also worth noting actually one of the things that led me to believe it might be a bubble phase is not only the temperature dependence as well. If you'll notice here, the lower temperature at which it's observed decreases as you raise temperature, and also as you raise density. So, but that's, I guess, an aside. Anyways, if there's any more questions, thank you very much.